The field of text-to-video generation has developed thanks to advancements in text-to-image models. However, when it comes to generating humans, certain issues arise. First, some action must be captured from specific angles to be properly represented. However, as seen in the first row of images, videos where only the back view is shown can make it difficult to understand the action being performed. Second, there is a problem with the inability to control the extent of the camera's zoom on the subject. For instance, when inputting the prompt, a person punching on the beach, an excessively zoomed image of a person was created to the point where it was not recognizable as a person. Third is the inconsistency problem between consecutive frames. For example, when a prompt, a man, Gulf on the desert is entered, an issue arises where a person appears and then disappears. These problems can be addressed by models that provide additional conditions in the form of text guidance. The challenge is to generate appropriate skeleton that fits the prompt. It is a very tough job to manually create such detailed guidance. Therefore, we aim to generate 3D human motion from the text and then use this as a basis to solve these problems. These issues can potentially be resolved by models that incorporate text guidance as an additional condition. The challenge lies in creating appropriate skeleton that aligns with the prompt. The task of manually crafting such precise guidance is exceedingly arduous. Therefore, we intend to generate 3D human motion from text and use this as a foundation to solve these problems. Our proposed framework is as follows. We generate a sequence of 3D skeletons from text using off-the-shelf text-to-human motion generation model, then project these skeletons. Subsequently, we employ a post-guided text-to-video generation module to create corresponding video. In essence, our method utilizes only a text prompt to generate a video of a person that corresponds to that prompt. Moreover, our model can project sequences of generated 3D skeletons using a defined prompt, allowing the skeletons to be displayed as desired. By utilizing this, when creating videos with skeleton guidance, the direction of the projection is also reflected in the generated video. This is a qualitative comparison of the results when using other text-to-video generation models in our method. First, looking at the result generated by the prompts, a person clapping with hand on the moon, we observe the model scope only generates hands that are not clapping. The problem of generating only hands also occurs with zero scope. Gen 2 by Runway produces a nearly motionless video, which doesn't seem to depict clapping. T2V0 similarly encounters the issues of only generating hands, and the appearance of the hands is also far from a clapping motion. However, when our method is applied to T2V0, we can confirm that the entire figure of a person is generated, clapping naturally. For the second prompt, a person sits down and then gets up and goes back to the same place on the beach. Model scope generates a person, but the video is inconsistent with the content of the prompt. Zero scope has the issues of not generating a person at all. Gen 2 once again produces a video that is almost static, not performing any sit down or get up actions. T2V0 creates an object that is not a person, which cannot be considered a video corresponding to the prompt. However, with our method applied to T2V0, a person is generated that completely matches the prompt, and the movements are natural. This shows our qualitative demo, not as frame but as a video. Our method generally yields better results compared to other models. This clearly demonstrates the superiority of our approach over others, particularly in terms of naturalness of generated human figures and the dynamism of their movements, ensuring consistency with the prompt. This presents quantitative results when our method is applied to T2V0 and follow your pose versus using other T2V methods. AC stands for Action Classification Accuracy, which is a measure of how well the generated video matches the action specified in the prompt. FC stands for frame consistency, meaning the average cosine similarity between consecutive frames. It is a measure that decreases with sudden and unnatural changes between frames and increases when such changes are absent. CS stands for clip score, which indicates the alignment of the generated video with the prompt. Higher values in all three metrics are advantages, and our method outperforms all other methods. Additionally, Table 2 shows the results using off-the-shelf text-to-human motion generation models, T2M-GPT and MDM, with T2V0 for text-to-video generation. In essence, our methodology has the advantage of flexibility, with the potential for improved results as better T2M and T2V models become available. We conducted a survey as part of a user study and found that in most cases, our methods significantly outperform others in terms of the relevance between prompt and the generated video, the realism of the created motion, and the overall quality. This slide illustrates the results of projecting with camera movements during the projection process. We applied camera motions such as translation, rotation, zooming in and out, and then used T2V model to create the video. It can be observed that the background does not change, which is a limitation of the T2V model itself. However, this is an issue that can be resolved as technology advances.